so when we're kind of approaching the end of this summer school, and so this is the final mini course today and tomorrow morning. And it's called Singular ODEs and the Stokes phenomenon. So the topic is, so I want to talk about basically singular ODEs, by which I mean linear ODEs in a complex domain, so it sounds pretty simple. But they have singularities, so I will allow poles in the coefficients of these differential equations. And so that kind of leads to interesting phenomena. And in particular, the phenomena that I will aim for, hopefully we'll get to discuss it to some extent at the end of tomorrow, is this these two words, Stokes phenomenon. So it's kind of an very interesting mathematical phenomenon which appears very naturally in the study of singular ODEs, but it's really widespread in mathematics and physics. Okay, so let me jump right into it, give you a definition of what we're talking about. So let me take a domain, U in the complex plane. So I have a complex plane with coordinate Z. A domain, so open, connected subset. So a neuromorphic differential linear system on U. So this is the term that I'm defining. And usually I'll just say differential system or linear system or just system. So is a system of linear ODEs, a system of linear first order ODEs. Form this. I'll use this symbol nabla. So nabla, so this is going to be my differential operator applying to y. So the formula for this differential operator is, so there's the first derivative term, and then there's the matrix of coefficients, which I'll call A of z. And so this is multiplying y. And so I'm looking for solutions to this first order differential system. So here, y is supposed to depend on z, and it's a z-dependent vector in c to the n. So this is the unknown function. And usually I will want this function, when I'm searching for such a function, I will want this function to be holomorphic, or holomorphic at least, away from certain points. These points, they will be called singularities. So a point z naught, I also need to tell you what A is. So, and A, so A is a matrix, Aij. So it's an n by n matrix. Of meromorphic functions on U. So these coefficients are all meromorphic functions. So I will often write this by saying that A is a map from this open set U to the space of n by n complex matrices, which is the little GLNC, which I will also just write GLN like that. And this is a meromorphic map. So points where this map has singularities, so the points where it has poles, it's a meromorphic map, so it may develop poles, or in other words, points in U where at least one of the coefficients Aij has a pole. Those are going to be very special points, and so we'll give them a name. So a point, somehow we'll be particularly interested in those points. So a point Z0 where A has a pole is called a singularity. Of this differential system. So what makes these ODEs singular is that I'm allowing these special points to enter the picture. Okay, and I immediately see that there's a problem with the proposal, because now I want to slide this board over so that this part of the board is comfortable for me, but that covers the previous board, so there's no magic solution. So, let's try to crouch. Right. Okay. So let me give you a bunch of examples so you have an image of what we're talking about. So here's a kind of a random differential system that I wrote down. So we have d by dz minus, here's a matrix, 1 over z, whatever, z squared, sine z, what else did I write? Z e to the z. These are just pretty kind of random functions I chose. So this thing is, the coefficients of this are all well defined, in fact, on the whole complex plane. So we know that this is an entire holomorphic function. These are all entire holomorphic functions. This is a function that is defined everywhere on C, but it has a pole at z equal to 0, so there's a singularity. So pole, it's a simple pole at z equal to 0. So if in this example, if I replace, maybe let me just use a different color. If I were to replace, let's say, this coefficient e to the z with e to the minus z, sorry, with e to the, not minus z, with e to the 1 over z, so if I did this, then this coefficient now has a singularity at z equal to 0, but it's not of a pole type, it's an essential singularity. And so, this differential system with this replacement, that would not be an example of one of the ones that I'm talking about. So it is not meromorphic on C to the Z. But you could say, now I'm running out of space, just continue here, but you could say nabla is meromorphic if I just remove that point on U, which is C to the Z minus the origin. So I'm just giving this example just to kind of give you a feel for what the definition is saying and what it is not saying. So a lot of very famous equations from mathematical physics, like classical equations from mathematical physics, fall into this type. So I'll give you one example. So for instance, the Gauss hypergeometric equation. Very famous in mathematical physics. So if you've never seen it, it's an equation of second order. It's a second order equation, which is normally written like this. It's a family of equations, in fact, because it has parameters. And one way to write it is like this: a, b, y is equal to 0. So a, b, and c are complex numbers. So there's an entire c to the 3 family worth of these equations. And it's defined on the whole complex plane. And the way I see that this second order linear ODE gives me an example of a linear first order system is by a very simple trick that you probably learned in your calculus or first year ODE course, where you just replace, you introduce, so you introduce a vector variable, capital Y, where the first entry is just the function y, and the second kind of unknown variable is the derivative of y. This trick, you may have seen this trick. So if you do this, so what you need to do is you need to differentiate this, right? You apply the derivative to this vector, and you get y prime here and y double prime here. And so now you have an expression for y double. You can solve this equation for y double prime and plug in. So the system that you get looks like this. Over z minus 1, a plus b plus 1 z minus c over z minus 1 with a minus. So this is just the last coefficient with a minus, and this is just this coefficient with a minus. And I've divided, you have to divide by the coefficient in front of the second derivative. So this guy has singularities quite obviously at z equal to 0 and z equal to 1. And so, similarly, like equations, so I mentioned equations from mathematical physics, but your favorite equations like Bessel's equation or Weber, they all fall into this scheme. They're all second order linear ODEs with singularities, and you can transform them or write them equivalently as first order systems, and so they all fall under the remit of this definition. Okay, let me give you one more example. So far we've just seen poles of order 1. Let me give you an example of a pole of order 2. So here's a system, z squared minus 1, 0, 0, 0, 0, 1, 0, 0, 0. So this one, you can see, has a first order pole, but more importantly, it has a second order pole. Anyway, this example in particular will be very, very important to us tomorrow, so we'll return to it. Let me give you another example. So here is an example of a kind of a system which is very easy to solve. You could say these are differential systems. How is it possible to solve them? So here's an example of a system which is very easy to solve because it is uncoupled. So this is my system. So there's a pole at Z, and the matrix is actually diagonal. And these lambda 1, lambda 2, they're just complex numbers. So the cool thing about this is that this is uncoupled, as I said, which means, so the matrix is diagonal. And so that means that even though this is a system of size 2, the two first order equations that make up this system actually are not interacting. So I can just solve them separately and get a solution. So I promise this is going to be more or less the most difficult differential equation we'll solve in this mini course. So if I write them kind of in a more familiar way as actual first order linear scalar differential equations, you get a system like this. And so what do you think is the solution of, let's say, this one? What kind of function y1 of z can I plug in here to get a true equality?
Exponential?
Yeah. So, the way I promised you, this is the hardest equation we'll actually solve. So, study of singular ODEs is really not about solving singular ODEs; it's about studying their properties, which is a very geometric and algebraic set of techniques. So, the way you solve these things normally, just to remind you, is I think they call it separation of variables. So if I put y1, if I divide both sides by y1 and I divide the right hand side by and I divide both sides by z as well, then what I can do is I can now just integrate both sides, and I see that so the left hand side gives me log y1, and the right hand side gives me lambda 1 log z plus constant. And so now if I exponentiate both sides, I get my solution, which is which I can write as let's say some constant like this. Does that make sense? So one reason I wanted to write this explicitly is so that you can look at the form of these equations and notice that whenever we have a behavior in our system like this, whenever we have a pole, our solutions behave in a kind of in a similarly singular fashion. So these functions are genuinely singular unless lambda 1 and lambda 2 are both equal to 0. We're having a logarithm, so there's a logarithmic singularity at z equal to 0. These solutions may blow up as z goes to 0 because if the real part of lambda 1 is negative, then this will behave kind of like 1 over something that's becoming very, very small. These are also not single valued in general, unless lambda 1, lambda 2 are integers. You would need to draw, they're only properly well defined in the complement of some kind of branch cut. So all of these phenomena are present as soon as your differential equation has a singularity. So what we normally like to do in this theory is to put, like, when we try to solve a differential system, we try to put sorry, let me say this differently. So if I look at the general solution of the system, so the general solution of this system is, of course, it's supposed to be a linear combination of the solution obtained from the first uncoupled system, uncoupled equation in this system, and the second uncoupled equation in this system. So I can write it as a linear combination of the two solutions. And the two solutions are, as we found them, z to the lambda 1 and z to the lambda 2. And what we ordinarily like to do is we like to put together all the linearly independent solutions into a matrix, which we call a fundamental solution. So a fundamental solution is just a matrix of functions whose columns define a basis of solutions. Is this okay so far? Any questions? Just giving you a little bit of time to think if you have a question. All right, so last example, we're actually going to do something to the last example. So let me give you a very concrete system. So by the way, I'll often just omit writing the y, and I'll just tell you what the differential operator is. So the system I want to study looks like this. So this is a system over the whole complex plane, and clearly it has simple poles at 0, 1, and minus 1. So this system is not uncoupled. So solving, it's not of this form, it's not diagonal. So it's not so easy, at least a priori, not so easy to solve it. So, but suppose I do want to solve it. So to solve this thing, what do I do? I'm basically facing, if you want to put it in kind of slightly more familiar terms, I'm facing a system of two first order equations, but they're coupled. Each one is coupled, so it's hard. when you have coupled differential equations, it's not so easy to work with it. If I could somehow uncouple this system, then it would be just as easy to solve it as this one. So what does it mean to uncouple? Well, one way to uncouple a system is to kind of do something, transform your unknown variable in a way that absorbs this coupling in some way. So try to change the unknown variable y. So what does that mean? You go from y to some new variable y naught, let's say, given by, so the most typical way in this business is to multiply, introduce a matrix G. So where G is allowed to depend on Z is some kind of, GL, well in this case GL2, but in principle GLN matrix. So invertible matrix. And sorry, there should be a knot here. And holomorphic. Because if I'm trying to recover holomorphic solutions, I would like to ensure that whatever transformation I apply to these holomorphic solutions is also holomorphic. So, okay, so I tried this at home, and the one that leads to something interesting, so I'll let you try it for a few seconds, is this one, 1, Z, Z, 1. Okay, so now we're going to do a little calculation. So if I'm trying to solve this equation, this equals to 0. Now the idea is that I'm going to replace y with a new variable, y naught, which is related to y by that identity. So let me just shove that in. Right. Okay, so what does this mean? Let's continue. So, I'll call that matrix A. Yeah, so what are we doing? So we're doing this. G, why not? Okay. So I need to, there's a product rule. So what do we have? We have del Z G, that's a new matrix, times times y naught, plus G times del Z y naught, minus, now this is just ordinary multiplication of matrices, A, G, y naught. Right? Okay, let me collect the terms. What I see, this is still a linear differential operator acting on y naught. I want to write it that way. So I have G del Z minus AG, this bit, and then this bit, plus del Z G. And all of this is acting on y naught. So now what let me do is factor out g. So I just want del z as my differential part, so I'll just factor out g. And what I have is del z minus g inverse a g plus g inverse del z g acting on y naught. And so this is perhaps something I will call nabla naught. So that's my new differential system. What I did was I changed my unknown variable by some, at this point, unspecified matrix G. And what what that operation has done is that it's changed the differential system for me. And now, the idea being the following. The reason I embarked on this journey was that the matrix A was just a little bit too complicated for me to handle, right? But here, in this newly transformed differential system, there's a lot of operation happening on the matrix A. Like I'm conjugating A, and I'm also kind of adding some kind of term which is given by G. And so the hope is that if I can guess, if I can pick matrix G correctly, then I can simplify my matrix A by using these operations. So, so this is what I'm suggesting this matrix G is meant to do. So I encourage you now, whilst I erase the board, to literally now take this G and plug it in here. Just to help you, how do you compute? So in here, one of the things that you need to compute is the inverse of G. There's a quick and dirty way to compute the inverse of a square matrix. There's a 1 over the determinant, which is 1 minus z squared. That's the determinant of G. Times you keep the diagonals, and then you swap these two, which are the same, and multiply them by a minus. That's the quick and dirty way. Right, okay, so just try your hand at this calculation.
Yeah.
So more of a physics question. Can we interpret this as some kind of gauge transformation?
That is exactly what it is, yeah. This is a motivating example for precisely that.
Okay, so wherever you are in that calculation, if anywhere, I'll let you complete it on your own. So if you do plug in all your matrices and compute them, what you get in the end is that, so it follows that nabla naught, this transformed system, is of a exceptionally simple form. It looks like this. This, of course, is no accident because I chose it that way. Of course, you know, we just solved this. This is an uncoupled system, so it's super easy to solve. So nabla naught applied to y naught is equal to 0, so the solution is that y naught is this matrix z to the lambda 1, which in our case is just 1, so it's z, and z to the lambda 2, which is minus 1, so it's 1 over z. And so to get, now how do we get the solution of our original system? Well, y is just g y naught. So I just need to multiply that matrix G by this matrix y naught. And this is very simple, z, 1, z squared, 1 over z. Like this. So I kind of, I want you to take a second and appreciate that we just did something slightly remarkable here, because we solved a coupled system of two equations, albeit linear, first order. Nonetheless, they're a coupled system. That you can think of it as a second. It's essentially something like a second order differential equation. So those are not easy to solve, but we solved it without ever really solving any differential equations. I mean, the only differential equation we solved was that y1 prime was equal to zy1. That's the only differential equation, more or less, that we solved. Yeah.
How would we know to use this g in particular?
Yeah. Right. Okay. Yeah. For that, we'll get to this. That's exactly the point. Yeah. But nevertheless, all we did was just a bunch of matrix multiplication, and we got ourselves a cute-looking solution of that system. So the upshot is that we found this matrix G such that nabla, such that we were able to write nabla as essentially a conjugation. Right? Is this obvious? Maybe let me write it here. So just to continue this equation, so we have G nabla naught applied to y naught, right? That's what this equality says. But y naught is, if I multiply the left-hand side, if I multiply it through on the left, inverse. I can, again, rewrite this in terms of y. This is one of the many reasons why I insist that G is invertible. So the point is that we wrote it in terms of another system. This is the simplest system. That we can actually solve. Somehow this is always the name of the game. You're faced with a system, and your strategy is to apply transformations of this type. We call them gauge transformations. So apply gauge transformations in order to simplify the system as much as possible to a form which we can actually say something about. So this comes immediately with a warning. Which is basically evident from this formula. So I keep insisting that this G needs to be invertible. This matrix G needs to be invertible because, of course, we're trying to get a homomorphic solution. It needs to be like we're trying to get a basis. So if there's some point, some value of z where the transformation is not invertible, the basis won't be sent to a basis. So anyway, it's kind of fundamental that G remains invertible. But this matrix very evidently fails to be invertible because it has this factor in front of it. So at z equal to 1 or minus 1,
the inverse of G simply blows up, so G is just not invertible. So a priori, the solution that we found, this solution Y, because we used a transformation G whose, if you like, domain of definition is strictly bounded by, you know, these bad points at plus or minus 1, a priori at least, this solution Y is only valid within that range, and in particular, you know, I'm kind of secretly focusing here really on this point z equal to 0. So I'm really studying the behavior or studying the solutions of this system near this special point of interest z equal to 0. That system has other singular points like 1 and minus 1, and maybe, you know, maybe if I introduce another coordinate, you know, put it on a Riemann surface, that's another valid thing. There would be other points that could be interesting. But in this case, like in this calculation, I was really just interested in z equal to 0. So let me kind of put this in words. So a priori, such solutions make sense only near z equal to 0, near the singularity. So because determinant of G is 1 minus z squared, so G is not invertible at z plus minus 1. So the interpretation of this is that Y is really should be treated as a local fundamental solution of nabla near this point of interest z naught. And then, you know, of course, you could perform the same kind of analysis near another point and get a local solution there, and then study how local solutions near one point interact with local solutions near another point. These are kind of connection problems. That is not something that we are going to be talking about. So I from now on, I really want to focus on the local analysis of singular differential equations. So I'm going to focus on these special points, these singularities, and see how, you know, what these systems, what the behavior of these systems is like in the immediate vicinity of a special point. And our main technique is going to be precisely this kind of operation that we did, by which is to introduce a matrix G to simplify our system. So let me now introduce a bunch of definitions to kind of axiomatize this stuff that we've seen. So a gauge transformation is any holomorphic invertible matrix G. So it's a map from U to GLNC. The purpose of a gauge transformation, the reason we call it a gauge transformation, is that it acts on our system, and we call this action a gauge action. So the gauge action of G on a system nabla del z minus a. Let me say this one. Let me write it like this. So a system on U is given by the formula that we I've seen, except I'm just going to swap some signs around. So I'll use this notation when G acts on a differential system by gauge transformation. I'll use this notation. And what this is really just conjugation by G. And so then the formula is essentially as we've seen before, G A naught G inverse plus del Z G times G inverse. So this is my A. And then I'll say that two systems nabla 1, nabla 2, defined on the same domain, are gauge equivalent if there is a gauge transformation which takes one to the other. And I'll write it like this. Nabla 1 is equivalent to nabla 2. So if there is a gauge transformation G such that, let's say, nabla 2 is the image of nabla 1 under this gauge transformation. So a couple of notes. So we've already seen this, but let me spell this out. So if we have that two systems are gauge equivalent, then a fundamental solution of 1 really produces for you immediately a solution of the other. So nabla G to 0. Or maybe the other note that I should make is that, as the name suggests, this gauge equivalence is an equivalence relation. Okay, so this kind of gives us a goal now, which is to study differential systems by using gauge transformations, by using this so-called gauge symmetry. So what you do is you start with a system and you try to search for gauge transformations that put that system into kind of the simplest possible form. And in particular, you might want to find out if there is a kind of normal form. You know, if there are certain parameters in your system that you can identify that immediately, without much computing, can tell you whether or not the system can be put in some kind of very standard form that you can solve. So let me write it like this, maybe. So the goal is given nabla, find, how do I want to, let me write it like this. So find, quote unquote, good local fundamental solutions near a point z naught, some point of interest, normally a singularity, so first of all, we can always move this point of interest to the origin, so by moving, make things completely standard. Just applying an affine transformation on the z-plane, and then using gauge symmetry to put nabla into some kind of standard or normal form. So by this I mean, again, vaguely, the simplest possible form or simplest possible representative of the gauge class, the equivalence class of nabla, which maybe I'll call nabla square bracket. And so one more remark is that because I'm only interested in local fundamental solutions, we're only interested in kind of arbitrarily small local neighborhoods of this special point z0. So only interested in arbitrarily small open neighborhoods of z0. And so there's a tool in complex geometry, or in geometry in general, that is really helpful to work with such situations. And it's the concept of a germ of a neighborhood. Yes?
We mean by gauge symmetry just like, what do we mean by gauge symmetry is just using equivalence classes, right?
Yes, yeah, gauge symmetry, yeah, just gauge equivalence. Yeah, so there's a concept of a germ of a neighborhood, or what I will call the infinitesimal disk. Let me define what that is, a very helpful concept. So definition. So the infinitesimal disk which maybe I'll denote by D. So it's the equivalence class of all neighborhoods containing the origin. It's the equivalence class of all open neighborhoods U of my special point Z0, which I am now just assuming is the origin. And what is this, it's an equivalence class under what relation? So where any two such neighborhoods so U and U prime, so they are considered equivalent if simply their intersection is a neighborhood of Z naught. Again, equivalent if U intersect U naught is an open neighborhood. Which really is no restriction at all, because you have two open neighborhoods, they both contain Z naught. Their intersection is necessarily open. Their intersection is necessarily open, and so therefore necessarily defines an open neighborhood. But the way you should think of this concept of a, so sometimes people call this germ of an open neighborhood, or germ of C at Z naught. You should think of it as, so here is my point Z naught, and here are all of these neighborhoods of Z naught. They're all smashed together into one equivalence class, or in other words, each one of these open sets is a representative of this infinitesimal disk. So each, i.e., any open neighborhood of Z naught is a representative of an infinitesimal disk. Yeah.
With these G's, are you assuming that they're like compactly supported or something?
No.
Right. So like you could have a G that changes the winding numbers of like A.
Winding numbers of A. What do you mean by a winding number?
I guess if you're thinking like in the physical sense, normally you have like a connection and you have large gauge transformations that are supported at infinity, and this can change like your equivalence classes of your connection.
Sure. I mean, I am not placing any restrictions on how G behaves at the boundary of U. So in particular, if U is C, CZ, I'm not saying how G behaves at infinity. Yeah. I'm only interested in this open set, and in particular, I'm really just interested in a small neighborhood.
Is it reason you wrote Z0 to Z0 to 0?
Yeah, that's supposed to be an equality. So. I just mean that whatever special point you're interested in, you can always shift your coordinate system to put it at Z equal to 0. That's all I mean. So, right, so this D is really just open neighborhoods U naught of Z naught modulo, the equivalence relation that U is equivalent to U prime if their intersection contains Z naught. I mean, in this case, it's kind of almost tautological, but this idea of a germ, that's the word I keep using, a germ of an object, which is an equivalence relation over some kind of condition of this type. It's a very, very useful concept, especially when you try to talk about local stuff. So, any questions so far?
So do you assume that your G comes from a is there an underlying Lie group?
Sure, GLN. Sure, GLN. Yeah.
Sure. Yeah. Okay.
So when I speak of a function on an infinitesimal disk, so what this means really is just f is a function on some open set that represents this infinitesimal disk. 1 second. For some, if you like, no, like this. For some open neighborhood of Z naught. Yeah.
I'm a bit confused now. In the previous board, you wrote that D is an equivalent class, but then at the definition, at the equality at the bottom, it seems to me more like a kind of set of equivalence classes. You look at all open neighborhoods by some. I don't see why the bottom should just be one equivalence class. Why it couldn't be more than one. This here, yeah. I don't see why that defines just one equivalence class. It could be
Why you mean why this is
a single equivalence class and not a set of equivalence
well,
classes.
I mean, a priori it doesn't have to be, right? But in this case it turns out, right? So simply because if u and u prime, right, the condition is that u and u prime are open neighborhoods of Z naught, their intersection is necessarily an open neighborhood of Z naught. Any two open neighborhoods of Z naught have this property. Right? You could, for instance, well, anyway, yeah, I don't want to overcomplicate this.
But in this case, it is just one
It
equivalence.
is just one equivalence class. So any open neighborhood is equivalent to any other open neighborhood. But that's kind of that's what you should think of as the infinitesimal disk. It's the kind of smallest, crudely, well, slightly incorrectly, say it's the smallest possible open neighborhood of a point. It's not really an open neighborhood. It's the equivalence class of all possible open neighborhoods, right? So it's the arbitrarily small open neighborhood or arbitrarily small disk around the point. That's what this concept is supposed to capture. It's a very common way of dealing with local things in geometry. You restrict to the germ of a point, or you restrict to the germ of a subvariety, or you restrict to the germ of a sub manifold. These are very, very common concepts, and they're all defined exactly in this way. So even though here, admittedly, it's slightly tautological what I'm saying, because there is only one equivalence class. In general, there may be more. They may be more sophisticated, but they're all of this type. So I just wanted to expose you to this idea of true locality. And so and in a similar vein, when I speak of a function on this infinitesimal disk, a function needs an open set as its domain. That's not really an open set. It's the equivalence class of all possible open sets. But what I really mean by that is that there is some representative of this infinitesimal disk such that this function is defined. I'm not saying that this function is defined in every representative. I'm just saying there is some representative. Does that make sense? Again, it's very kind of it's a convenient almost linguistic tool. Right. So and then in particular, you could look at the space of all, say, holomorphic functions on this infinitesimal disk, and let's see. Let's try to figure out what they are. So we're talking about so the space of all possible functions, each of which is defined on at least some open neighborhood of the point. So what do we know about holomorphic functions? Holomorphic functions have a very important, essentially defining property, which is that a holomorphic function at a point admits power series expansion, the Taylor expansion, and it converges to it. So any holomorphic function at a point admits such an expansion, and any expansion, any convergent power series engenders a unique holomorphic function by analytic continuation. So let me just write this, and then you tell me if you're really confused by this. So the space of all holomorphic functions is really the space of all convergent power series. Convergent power series in Z. With complex coefficients, obviously. So any one of them represents a holomorphic function which is defined on some potentially extremely small open neighborhood of the origin. So this is a kind of an important. It's actually an algebra, but I won't really care about this algebraic structure. I'll denote this I'll use this fancy notation for this though, because we'll use it all the time. I'll call this set C of curly bracket Z. And so similarly, so if I have a system, so any system, you know, nabla del Z minus A of Z, defined on some open set containing the special point that I'm interested in, which I always put at 0, determines a system on the infinitesimal disk. So this is the concept that I really want to study now. So these are kind of truly local study of differential systems. And I'll write them like this. So a system, definition, a system on this infinitesimal disk D with, and you see, sorry, I wanted to make this remark before giving you the definition. The cool thing about doing this kind of complete, you know, extreme zooming into a special point is that if that special point is a pole, then you know, something we know about meromorphic functions is that poles are isolated. So, you know, I can never have like an accumulation pattern of poles. So if I zoom in, if I choose a pole and I say this is the pole I want to study currently, and I zoom in sufficiently tightly, then all the other poles are ignored. So I'm really just studying one pole, and everything else is nice and holomorphic and kind of irrelevant. So it's just that pole that I'm completely isolating that pole, and so that's why I'm making the definition this way. So a system on D with a pole of order M, an integer, is by definition going to be the following. So any differential system of the form, and I'll write it slightly in a slightly different form like this. So nabla applied to y. So I'm going to change my differential operator. I'm just going to take this pole, potentially pole of order m, and I'm just going to multiply through by z to the m. I'm just going to write it like this. The reason this is convenient is that because I am insisting that the pole, I'm just zooming in on one pole, and I'm insisting that that pole is of order m, that means that's the largest order pole appearing in the matrix A. Oh, sorry, if I wrote it like this, that would be the largest order pole appearing in this meromorphic matrix A. And so if I just multiply through by z to the m, I'm cancelling all possible poles. And what remains is just something holomorphic. So that's why I can write where A of z, is now a matrix of holomorphic functions on the infinitesimal disk, or a matrix of convergent power series. So I'll write it maybe like this. It's a matrix in GLN. It's an n by n matrix, but with coefficients which are convergent power series. i.e. an n by n matrix with values in C of Z. Does this make sense? Yeah.
I'm a bit confused about the definition of the space of holomorphic functions. I think, so like D captures something about Z naught. On the right hand side you don't have, like I don't understand how it's specified to the point Z naught.
The Z, well, I'm always putting Z naught to be 0.
Okay.
And this, you could say that this is, any holomorphic function of z, if you take its Taylor expansion at z equal to 0, it'll be of this form. If, if z naught is not 0, I would replace this with like z minus z naught powers of that. Just simplifying by putting z naught to 0. Yeah.
I get this idea of isolating the poles, but at the same time we also know that the solution can be expressed as a power series on a radius of convergence, so which is the distance between the pole of interest and the next one.
So that is, first of all, that is a hard theorem. And second of all, the reason you might want to do this kind of semi-global analysis is so that you can then connect it to a local solution developed in the same way at a nearby pole, right? So that is called a connection problem, and it's kind of a non-trivial, highly non-trivial. It involves transcendental functions. So. Actually, I don't know what was the question. I think I interrupted your question.
No, I'm just wondering why we need to go through this entire equivalence class of open sets if we can just say that instead of just looking at the function on this infinitesimal disk, we just look at it on the radius of convergence, so the distance to the next pole.
I see. Okay, so the reason I want to do this is because what I want to do now is I want to study the space of all possible systems, right? So
right. Okay.
So any one system, indeed, is defined on some open disk around Z naught, right? But it is not true that there is an open disk around Z naught of some finite radius such that every single system is defined on that open disk. That is not true. Just like with these functions, right? Functions any convergent power series defines a holomorphic function on some disk of finite radius, by definition. But it is not true that there is a disk of finite radius such that every convergent power series is convergent on that disk. You can always find a convergent power series which converges on a strictly smaller disk. Right? So that is the purpose of looking at arbitrarily small neighborhoods, because now I want to study the space of all possible systems. In other words, the space of all. Well, that particularly involves the space of all possible convergent power series.
So you're going to use gauge transformations to link both the differential operators as well as the kind of corresponding representative disks.
Correct. Yeah. Okay. Yeah.
Just small thing. Based on your definition, the order of a system can be negative, right?
The order of the system can be negative. Yeah.
Because for a function, it cannot.
Because what?
For a function, not a system, the order of a pole is positive always, right?
Well, yeah. I mean, if you could say that if a pole of order -1 is a 0. Well, does it make sense? A pole of order -2 is a 0 of order 2.
We have 10 minutes until the break.
Perfect. Yeah. Any other questions? Right. Okay. So, I mean, your question was precisely on time, because the reason I want to focus on this infinitesimal disk is so that I can introduce the space of all systems, which I will denote maybe by syst of M, N. So this is the set all systems of this form. And so you see, what is the defining object? Once I specify the order of the pole, once I specify this integer m, the only defining, in order to give you a particular system, all I need to give you is this matrix A, so an element of this, an element of this space. So So, in other words, what this discussion shows is that the space of all possible systems is isomorphic to this set, GLN with coefficients in CZ. It's really just a choice of this matrix A. Mind you, this is a big space. So these are n by n matrices with convergent power series. There are many convergent power series. Sorry, I shouldn't have erased this. So what is a gauge transformation in this context? So a gauge transformation in this context, so, or you can say a gauge transformation over this infinitesimal disk D is any invertible matrix with coefficients which are convergent power series. So it's GLN with values in CZ. And I'll give this set special notation. I'll maybe write it as blackboard G sub N curly bracket Z. And then the gauge action now becomes an action of this, what is a group. This is actually a group. So gauge action is the action of Gn Z on this space of all systems. And so I can look at the quotient, which I will write with a lowercase s, syst, mn. This is under that identification of the space of all systems. This is just the action, gauge action of GLN, of big GLN on little GLN, but with coefficients in convergent power series. So it's almost like, you know, the usual conjugation action on matrices. So the space of conjugacy classes on matrices, this thing. This is the space of conjugacy classes. So we're kind of studying a very similar object, but we're replacing the base set of scalars, which are complex numbers, with a different notion of scalars, which are convergent power series. And the action is, it's like a conjugation action, but it involves this differentiation. I think there was a hand up. Yeah.
Is little and big GLN the group in algebra, or?
Yeah.
Okay.
Yeah. This is the. So ignoring the coefficients, GLN is the Lie group, right? The general linear group, and this is its Lie algebra.
Thank you.
Okay. So this guy is the moduli space. Moduli space of systems of type Mn, by which I mean with all of order M and of size n by n. And so my goal now is to study these moduli spaces. I want to understand what they look like. So this is just a rephrasing of saying I want to now understand what systems look like up to gauge transformation. So what are the possible simplest representatives? How can I identify which simplest representative belongs to the same gauge equivalence class as my given system? These are essentially identical questions. So maybe just before we go on a break, let me make one observation. So there is an obvious map which increases the order m of the pole. So like this. How does it work? Very simple, just multiplication by z. So if I have a system which looks like Zn del z minus a, so that's a I can map this guy to what I could call z times del. So this is just z m plus 1 del z minus z times m. This, of course, this operation doesn't introduce any poles, right? Because if I multiply by z, now my new matrix defining this differential system has a 0 at z. So whatever the new additional pole order will get cancelled by that additional 0 order. And in fact, this is you can use this observation to identify precisely systems which have come from lower order systems by this map. So this is in fact an inclusion. Does this make sense? So in particular, this induces an injective map at the level of the moduli spaces. The way you can see this is you can just see that the gauge transformation. A gauge transformation will not, if there's a 0, a gauge transformation will not alter that 0. So I think maybe this is a good place to pause for a break. All right, so here's just a very quick summary of where we have arrived. So we've defined this space of all systems of type M in size n. So they were all objects of this form. So there's the z to the m times del z differential operator minus a matrix, an n by n matrix with coefficients which are invertible matrices. And so if I just take A from this expression, that gives me a map, which is a one-to-one map, to this space of n by n matrices with values which are power series, convergent power series. And there is a group, called gauge group. It genuinely is a group, which is the group of invertible n by n matrices whose coefficients are convergent power series. And this group acts on this set of systems by the gauge action. This is a group action. So now we have a set with a group action. What I'm interested in is studying the quotient of the set by the group action. So this is what I'm calling little cyst of type Mn. And again, under the identification of the big cyst with the space of matrices with convergent power series as coefficients or as entries, this is just a quotient like this, a quotient of this space by this group action, which is kind of very, very similar in spirit to something we are familiar with from linear algebra or from algebra, which is the conjugation action by GLN matrices on all matrices. And we know that, so I'm just talking about this GLN mod GLN, just the usual conjugation. And we know that this quotient is the space of conjugacy classes, which are Jordan normal forms. So we know that every n by n complex matrix is equivalent to its Jordan normal form. So this is the space of Jordan normal forms, essentially. And this is a kind of, if you like, generalization of this type of quotient, where instead of matrices, instead of constant matrices, I'm now considering matrices with coefficients which are some kind of holomorphic function or convergent power series, and the conjugation action is more sophisticated still. It's not just simply conjugation by a GLN matrix. It's also there is a differentiation, there's a derivative of this matrix.
So just to be clear,
yeah,
in that Jordan normal form you just mentioned there, you're saying it's Jordan normal form with coefficient. Power series in Z with coefficients in Jordan normal form, or entries are...
No. It is more. I'm drawing an analogy. Yeah. I'm not saying that this quotient is the space of Jordan normal forms of. So it is genuinely different because the action, there are many things which are very similar, but it is a genuinely different problem. They are going to be normal forms of some type. Some kind of form. So that's where I'm heading. I'm giving you this analogy that you should interpret this as Jordan normal forms, or in other words, certain types of normal forms of matrices. These are going to be certain types of normal forms of differential systems. That's where we're heading. Yeah.
Are we taking this like a division because we want to identify which systems are uncouplable, or like?
Not necessarily, but some normal forms. Basically, that's essentially what they do. Anyway, I think your question will be answered as we go through examples. Right. Okay. So let me go. Let me just now study these spaces for various values of M and N. So let's begin. Maybe part 0, where M is 0 or in fact negative. So that means we have no pole. So in other words, I have this system, Zm, some matrix A. And by using this map that we just discussed previously, I can multiply through by z to the minus m. And get a system of this form. Now, of course, M is negative, or M is non-positive, so this is still, I'm not creating any poles. This is a positive power of Z. So this whole thing is still in GLN with convergent power series coefficients. And so here's the fact that we need. It is pretty much the only analytic fact that is required for this whole study. And it's called existence uniqueness theorem. first order ODEs. So for any system, or maybe I should say, obviously this system is now an element of big syst 0n. So maybe I should have said this explicitly. The upshot of this line is that any element of big syst mn, where m is 0 or negative, is immediately, I can bring it to an element of this space. And so I'll just study that space. So for any system nabla, there is a gauge transformation such that nabla is gauge equivalent to nabla naught, where nabla naught is just the trivial system, d by dz. So A is equal to 0. So, quick explanation why. So it is because of the existence uniqueness theorem. So you can use, for instance, Picard method or any other kind of fixed point method to find the fundamental solution. Y nabla, and then put, I hope I got the power right, G to just be Y. Remember, Y is a fundamental solution, so it's an invertible matrix. So I'll just let G be that Y. So, very concrete example. Let's focus on n equal to 1. So we have, so our system, we're solving something like this, and our system is just del z minus a of z, some holomorphic function on the infinitesimal disk. So we've already solved an equation like this. So this was d. You do separation of variables. And so you find that y of z is some constant times the exponential integral from 0 to z, for example, of a of z. And so if I put g, little g, this is my gauge transformation for n equal to 1, little g, to be literally this, y of z. I think I got the signs right. Then what do I have? So if I conjugate, so if I compute this side, g del z g inverse, what do I have? So I just get del z g times g inverse, and so if I differentiate g, which is y, I just get a back, and then I cancel out the g. So this is precisely nabla. And so maybe, why can I take this to be the gauge transformation? Well, because it's the exponential, right? So this is kind of, for absolutely trivial reasons, it's an invertible G01 matrix. Does this make sense? All right, so that means when m is 0 or less, we don't get anything interesting. We could say that upon up to gauge transformation, yeah, here's how we can say it. Whenever m is 0 or less, every system up to gauge transformation is the trivial system. So there is only one system up to gauge transformation in each of those systems. So we can write it like this. So syst, our moduli space, syst m n. So all m less than or equal to 0. This is just a single point, which is represented by a trivial system. Just one point. Sense? Oh, sorry. Okay, let's study the next case. So this is the first interesting case. So m equals to 1. So that means our system has a simple pole. Z equal to 0. So that means that any system in syst 1n is of the form z del z minus a of z. A of z is a convergent power series, or matrix of convergent power series. And what is convenient is to write it, so to extract the constant coefficient of this formal power series, and kind of leave the rest out. So it's very convenient to write it like this: z del z minus a naught plus z b of z. So b of z is just some other matrix of convergent power series. Right, and this A naught is just a constant matrix. So this A naught is actually a very important object. So A naught, it has a name, it even has a notation. I'll call it res nabla. So as I said, it's a constant matrix. And it's called the residue matrix. Of nabla. So it's going to be an important, not quite invariant, but almost an invariant. Very important quantity associated with our system. So I'll leave this alone. So because I can always extract the leading order part, the constant part of this matrix, for any system I always get a residue matrix, and so this kind of gives me a map. In fact, a surjective map. Which I'll call the residue map. Surjective residue map. From cyst 1n to little gln, is the residue map, which just takes nabla to its residue matrix. So one question I can ask is, so this residue map is obviously defined on this space of systems. How does it descend to the quotient? So in other words, does the residue matrix persist once I apply gauge symmetries? So does res descend to the moduli space? So whenever you're studying moduli spaces as the quotients by some kind of symmetries, and you define some kind of map which maybe extracts some form of interesting quantity, useful quantity for your analysis, this is always a question you need to ask. Does this map descend down to the moduli space? So how does my map interact with the symmetries? So let's test this. So suppose I have a gauge transformation. And so here's what I'll do. Let me write this gauge transformation as follows. This will help. Again, this gauge transformation is a power series in Z, so I can extract the leading order part, and then the rest I'll write in this form. Z for some little GLN matrix with coefficients in convergent power series. And so it's this form that I'll use in order to compute conjugation. So suppose I want to calculate this and see this conjugated new system, its residue, how does that residue relate to the residue of nabla? So let's see, so what do we get? Let's expand this, so we get Z del Z minus GA G inverse minus Z del Z G times G inverse. And so all I'm interested in is the leading order part, right? The zeroth order in Z part of this big matrix. So in particular, this guy, this gauge term, this already appears at order 1 in Z, so it cannot possibly have any effect on the residue. Right, does that make sense? Yeah? And here, well, I just need the leading order part. So the only... If I write it like this, I hope you agree with me. So what you can get from this calculation is that the residue of this gauge transformed system is not the same as the residue of nabla, but there is a very constrained relationship between the two, which is that it is conjugated by the leading order part of the gauge transformation. So the residue of nabla is gauge invariant only up to conjugation. So, in particular, that means that you could say the residues conjugacy class is an invariant, is a gauge invariant. Or I will call it a local invariant. So schematically I can write this by saying that that residue map descends down to the moduli space to give me a residue map whose image is not quite in GLN, but in the quotient. GLN by GLN. So it takes the gauge equivalence class of a system and sends it to the conjugacy class of the residue. And this is in fact surjective. Because I can realize any system by choosing a conjugacy class. I can realize any system with that whose residue is in that conjugacy class. Okay, so the residue matrix itself is not an invariant. Its conjugacy class is invariant. And so in particular, the eigenvalues of the residue are a local invariant. So eigenvalues of the residue matrix are local invariants. And so for this reason, they also have a name. They're called local exponents. And that kind of these eigenvalues of the residue matrix in a system historically have been kind of very important players. So if you basically open any book on dynamical systems, they often talk about local exponents, or another term that people use are Lyapunov exponents. You may have heard of that. So that's all part of the same story. And in dynamical systems, they use these eigenvalues to kind of predict long-term behavior of systems and stuff. And it's kind of very similar phenomenon here. So, okay, so I want to talk about these invariants. So if I have a system and I can extract its residue matrix, and let's say even look at the eigenvalues of the residue matrix, could I use that to kind of completely nail down what the gauge equivalence class of that system is? So let me phrase it this way, so put it as a question. Is the conjugacy class of the residue matrix a complete invariant? So, in other words, this map, which sends the gauge equivalence class of a system to the conjugacy class of its residue matrix, we know that it's surjective. Is it injective? So is the map injective and therefore an isomorphism? To put it even more concretely, if I have two systems, let me call them nabla prime, in 1, comma n. Suppose I have two systems. Suppose I compute their residue matrices. I find that those residue matrices have, let's say, the same eigenvalues, or more generally have this, have the same Jordan normal forms. So if that's the case, does it follow that these two systems are in fact gauge equivalent? So if I were to make this very simple calculation, extract residue matrices, compute their normal forms, figure out that they are conjugate to one another, does that guarantee me that there exists a holomorphic gauge transformation big G which will take one system to another? So let's examine this. So again, let's consider the case n equals 1. So in this case, my system is not really a system, it's just a scalar equation that looks like this. A naught minus z b z, where a naught is a number and b of z is a convergent power series. So this a naught is the residue matrix, 1 by 1 matrix, so it's just the residue of this system. So let me now consider another system, much simpler system with the same residue, where I'll just ignore b. So I look at z del z minus a naught. So consider this. So a question that we're asking is, does there exist a gauge transformation G, which is just, it's an invertible power series in Z, such that G applied to, let's say, nabla naught is 9. Well, so let's see. So let's just do this calculation very quickly. So what is this guy? So this is, so there's the differential operator still. And then we have G A naught G inverse plus Z del Z G times G inverse. Right? Okay, so G is necessarily a scalar function. A naught is just a number. So of course all of these now commute, they're not matrices. So in particular G and G inverse, they cancel out. And so what I have remaining is Z minus, Z del Z minus A naught minus a term that looks like which is the logarithmic derivative of G. So, in order to find such a G, all I need to ensure is that this term is equal to Z B of Z. So in particular, this thing, this logarithmic derivative of G needs to equal B of Z. That's the equation that we need to solve. And so that, of course, is very simple. G, again, it's one of the only differential equations that we know how to solve. G of Z is the exponential, the integral 0 to Z of B. For example, any constant multiple of this will do. And so this is clearly an invertible power series. So this is indeed whatever, a GL1 matrix with values in convergent power series. Yeah.
How did we get log G?
How, sorry?
How did we get log G?
How did we get log G? Oh, it's just because there is a, you know, this term is just dZg over G.
Okay.
So if you differentiate log, you get derivative of G over G.
So, I just want to ask, like, in what sense is that invariant local? Is it because it only depends on the first?
So here, yeah, so okay, so when I say local, it's because we're studying kind of a very local properties of these systems. So let's just use this as a definition, yeah. In general, these systems may be defined on some big, interesting, possibly compact holomorphic manifolds, and then there would be a distinction between local invariants, which have to do with localized data, like what we're doing here, and global invariants, which have to do with maybe some kind of monodromies around interesting topology. So that's the main distinction. Okay, so right, does this make sense? So what we found from this very simple calculation is that for n equal to 1, the residue is indeed a complete invariant. Why? Because any system that you can write down whatsoever with this residue is equivalent to this normal form. So maybe I will call this our first example of a normal, our first non-trivial example of a normal form. Oops. So again, diagrammatically, I can write this by saying that this moduli space of syst 1, 1, right, so m equals to 1, n equals to 1, is isomorphic to the space of gauge equivalence classes, each one with a special representative given by the normal form. And so the cool thing is that kind of clearly, by essentially the residue map, this moduli space is isomorphic to just a copy of C. I'll give you a few seconds to absorb that.
This calculation did not depend on the order of the pole, right?
Sorry, say it again?
All of these did not depend on the order of the pole so far.
Well, I have assumed that the order of the pole is 1, but indeed, we'll next move on to higher order poles and we'll see that something extremely similar is happening. But the fact that for this particular statement, the fact that I chose n to be equal 1, that is important. As I will now discuss, arbitrary n, it's not quite as simple. It has a similar flavor, and there is an open subset which is very, very similar looking, or has a very similar behavior, but it's not quite as simple. Any other questions? Okay, so let's now consider arbitrary n. So what we have is a system like this, z del z minus a naught, that's the residue matrix, minus z b of z. And let me kind of, motivated by this example, let me consider a candidate normal form to be just of the form where b gets eliminated. Something like this. So, so let's kind of try and retrace our steps in a similar way. So let's look for a gauge transformation. G, which again I will write. Do I want to do that now? Maybe later. Yeah, so let's just say G gauge transformation such that G sends this normal form to D. So what does that mean? So let's just that that means that the right-hand side. Let me write the right-hand side first. Oh, sorry, no. What am I saying? We have G A naught G inverse plus del Z G times G inverse. So that's the way G acts on the trivial system. Sorry, not on the trivial, on this supposed normal form system. And then that should equal to the matrix of Nabla. Should be this. A naught plus Z B of Z. I think we got this right.
G of Nabla 0 should be Nabla, right? Not
G of Nabla 0. Yes, thank you. I was looking at it and I was like, something's wrong. Right, okay, so now I'm going to massage this equation a little bit.
Sorry?
Yeah.
Sure. You're missing a z in front of the delta z.
Yes, thank you. That's very important, yeah. Was it the same? Yeah, excellent. You know, they say this is a kind of a teaching technique to randomly insert small mistakes just to keep everyone on their toes. Because if everything is so clear, then there's this phenomenon with I'm going off on a tangent, but Richard Feynman is kind of celebrated as like an amazing speaker, but all of his students always complained that they would come into his office for a meeting and he would explain to them whatever his thoughts are, and everything would be like super clear and like amazingly explained, and then they would come out of the office and just complete blank. They can't retrace any of it. So anyway, right. So so I'm going to massage this. So what I will do first is I want to multiply on the right by G, just to get rid of these G inverses. So let's do that. So I have G A naught plus Z del Z G is equal to A naught G plus Z B G. And right, and now the next thing I want to notice is that I have, so here I have G A naught, and over here I have A naught G. So if I bring one or the other to the other side, it looks like a commutator. So let me write it that way. So we have a commutator between G A naught. Actually, sorry, let me write, I want to write it slightly differently, just with a minus sign, for some reason. Reason being that that's what I wrote in my notes. And it's always a bad idea to go off script. Okay, so anyway, so this is the equation that we have. So if we are to find a gauge transformation G, which sends Nabla naught to Nabla, then we better look for an invertible matrix G which satisfies this differential equation. So, you know, on the face of it, I haven't really, like, if my goal is to, let's say, solve Nabla, right, which would involve solving some kind of complicated system of ODEs, coupled ODEs. On the face of it, I haven't made any improvements. I've just replaced one complicated-looking differential equation by another complicated-looking differential equation. But there's something, we'll see that actually we will be able to solve this without ever solving a single differential equation. So, and the key to this is that we will expand this equation star in power series in Z. So, so now let me write G as a power series, G sub k Z to the k, and so these G sub k are, this is what we're looking for, this is what we're trying to determine. I will also write B as a power series. And right, and so now we examine our equation order by order in Z. So let's start where we should start, which is the 0th order. So let's look at this equation to 0th order in Z. So this derivative term, that disappears because it already sits at order 1. The right-hand side also gets killed because it sits at order 1 in Z. So the only contribution to the 0th order comes from this term, and that is literally just the commutator between A0 and the leading order part G0 of our gauge transformation. So the task is to find a G0 which satisfies this, notice very much not a differential equation. So anyone care to guess the simplest possible choice for G0?
Multiple to the identity? Multiple of the identity?
Yeah, what kind of multiple?
Like a constant?
What kind of constant?
Complex constant?
One? Yes, just the identity. So, yeah, indeed. So just G0 to be literally the identity matrix, and that, that does it. So it's really that simple. Okay, but now you say, oh, fine, okay, but now that, now we go to the next order and you see that, the derivative aspect of the differential equation, that appears at order 1 because there's a Z in front, and right, so that's where differential equations are now going to start appearing. Well, let's see what we actually get. So let me look at the first order in Z. Okay, so yes, indeed, we get a contribution from this term, right? So we've expanded G as a power series in Z. So the derivative of G, which, right, so the only thing at order 1 in Z that would be contributed is something at order 0 in Z, in this matrix, derivative of G, right? So which term is that? G1, the constant matrix G1, which is as of yet unknown, is the only thing that gets contributed to this term. So we have G1, right? Now what about this term? Yeah, G1, right? So we need a contribution that appears at first order, so it's just G1. So we have G1 minus commutator of A0 with G1. And then the right-hand side is what?
B0, G0.
B0, G0. G0 is the identity matrix, so it's just B0. Beautiful. Let me call this equation double star. Okay, so the task is to find G1, an invertible matrix G1, which satisfies this equation. So this is maybe not strictly speaking, a very simple equation. It involves a lot of matrix multiplication. But at the very least, this is not a differential equation. It is a linear, this is a problem in linear algebra, right? We're solving a differential equation by solving problems in linear algebra. How cool is that? So, okay, so here's a fact from linear algebra, which is a very cute fact, which is helpful in, which is actually very helpful in even in like representation theory, so in seemingly unrelated subjects. So it's very good to know if, even if you don't care about differential equations or differential systems. So here's the really cool fact. So if I take any two n by n matrices, A, B, constant n by n matrices, and I look at the following map, which is, it's kind of like, well, the following map, so I'll call it maybe add AB, stands for adjoint. So it takes a GLN matrix to a GLN matrix, and it's the formula is like this. So it takes a GLN matrix X and forms the following matrix AX minus XB. So you see, if, for example, if A equals B, then this is just a commutator between A and X, and that is traditionally what is called the adjoint map. So hence the notation. Okay, but so there's two facts about this map. So first of all, this is a linear map. I mean, that's pretty clear, right? If I multiply x by a scalar, these are matrix multiplications, the scalar will just pop out, so it's linear. And if I apply it to a sum, you can distribute them, and you'll see that it's linear. So that part's very obvious. But now what's not obvious is that the kernel of this map has a very important property which will be very helpful for us. So the statement is that the kernel is trivial, meaning that this map is an isomorphism, i.e. add A, B is an isomorphism. If and only if a condition on the two matrices A and B, or more specifically on the eigenvalues of the matrices A and B. The two matrices A and B have no eigenvalues in common. The proof is very simple. You just show that this linear map, this is a linear map, so I should be able to write down, you know, whatever, big matrix for it. And I should be able to compute the eigenvalues of this big matrix. And it turns out that the eigenvalues of this big matrix are just the differences between the eigenvalues A and B. And so if A and B have no eigenvalues in common, then all the eigenvalues of this big matrix are non-zero. And so it must have. Okay, how is that going to help us? Well, it's going to help us because the left-hand side of that equation double star is exactly of this form. So let me rewrite this. Sorry to come back to this, but let me rewrite this. So I'll write this as sorry, yeah, my minuses are really screwing things up. I need to multiply everything by minus to find the roll, so I have. I think that's correct. I think that's the same equation. So using this fact, so if A naught minus 1 and A naught have no common eigenvalues, or said differently, if no two eigenvalues of A naught differ by 1, then we know that, we're looking at this equation, then we know that this linear map, which sends G1 to this combination, has 0 kernel, and so there must exist an element G1 in its domain, which is mapped to this element in its codomain. So, in other words, there exists, in fact, unique matrix G1, constant matrix G1, satisfying double star. So by making this assumption on slight assumption on the eigenvalues of the residue, I'm guaranteed that I can find the first order of this gauge transformation G. Does that make sense? Right. Okay, let's continue. I shouldn't have erased this equation. That's okay, too late. So now let me do one more step. Let me examine this equation at order 2. I won't do it as slowly, because I think now you kind of have a better sense of where I'm going. So at order 2, that equation, so if you just examine it, what you'll see is that you get 2 G2 minus the commutator and the right hand side is like B G1 plus B1 G0, which is just the identity. And so I can write this again in a similar form to that as A0 minus 2, A0 minus 2, G2 minus G2 A0 is equal to whatever, minus the right hand side. And so again, we can use this fact. So by making an assumption, so if no two eigenvalues of A0 differ by 2, then we are guaranteed by that linear algebra fact that there exists a unique matrix G2 which satisfies this equation, which is now, I guess, triple star. And so on. So I can keep going like this, and at every order, in order to apply the same fact and get a guaranteed element Gn or Gk at every step k, I just need to ensure that no two eigenvalues of A naught differ by K. But because, of course, A naught has finitely many eigenvalues, I'm guaranteed that at least at some process, at some step in this process, that condition will be definitely satisfied for all K following. So systems like this are very famous. Let me give you a definition. Next board. So this is what I'm leading to. What I was leading to is the notion of resonance, which is very familiar in the study of dynamical systems. So a system nabla is called resonant if the residue matrix of nabla has a pair of eigenvalues which differ by an integer. Has a pair of eigenvalues, some kind of lambda I, lambda j, such that lambda I minus lambda j is an integer. So if any of you have ever seen kind of the notion of resonance in dynamical systems, and perhaps wondered why the definition is somewhat nebulous like this, referring to some kind of integer differences, now you know it comes from this gauge transformation construction. So the opposite is that otherwise, so if this doesn't happen, if no two eigenvalues differ by an integer, nabla is called non-resonant. And so this defines a subset of systems, of non-resonant systems, which maybe I'll denote like this. So these are non-resonant systems. And well, we didn't really discuss any kind of notion of topology on this space, but there is a convenient kind of very natural notion of topology on this space of all systems. And with respect to that topology, you can say exactly why this subset of non-resonant systems is in some sense almost all the systems. So it is open dense. It's an open dense subset. And right. So that's not to say that the complement of this subset, so the set of resonant systems, is some kind of trivial thing. Or quite on the contrary, it's a very, very interesting set. It's just it's high codimension subset, but it is extremely interesting. And but anyway, right now I want to focus on this open dense subset, because for this open dense subset we can say something kind of neat. So this is a theorem, which we've kind of parts of it we've sort of seen with our own two eyes. So part one is that if I have a non-resonant system, then there exists a unique gauge transformation, or let me put it like this. There exists a unique power series, invertible power series, with leading term being just the identity map. such that if I take this power series and apply to nabla naught, where nabla naught is the same system as nabla, z del z, or rather, sorry, the nabla naught is this what I call kind of normal form, which just has the residue term, the residue matrix, and nothing else. So there exists a unique gauge transformation G. Maybe if I write this again, Z del Z minus A naught minus, what was it, ZB of Z. This is A naught. So there exists a unique gauge transformation. There exists a unique power series of there exists a power series with matrix entries, and whose leading term is the identity matrix, which gauge transforms this standard system into.
So again, G of nabla 0 is nabla, not G.
It seems to be a recurring feature. Thank you. What we didn't, by doing this calculation, you can kind of see that indeed this power series does exist. What we didn't prove, which requires a little bit of extra work, but it's really not so complicated, is to show that this power series is in fact convergent. This is a convergent power series, and so we get a genuine gauge transformation. So in fact, G of Z is a convergent power series. So G really is a gauge transformation. And so what that means is that any system nabla, any non-resonant system nabla, is gauge equivalent to this standard form, or a standard form of this type, where you just have the residue matrix. So one way you can say this is that the residue map defines an isomorphism. So if I look at the moduli space of non-resonant systems, so this is a subspace of all systems, there is an isomorphism between it and G. No, sorry, that's not quite true. There's an isomorphism between it and a subset of this quotient, which is made up of, let me call it like non-resonant Jordan normal forms, non-resonant diagonal matrices. So to put it another way, maybe that this syst part is isomorphic to the set of gauge equivalence classes, each of which look like this. So there are all these nabla naught n are just complex numbers satisfying the non-resonance condition. Sorry. Does that make sense? Yeah.
In this case, I guess the topology of system 1n is just the topology of GL 1c.
Well, it's slightly more complicated because remember that this is the quotient of this GL C Z. So you need. I mean, you could treat this as an infinite dimensional vector space, and that has a type of topology, and you could descend that topology, but I don't want to get into that. Yeah.
Why couldn't this matrix, the diagonal, why couldn't it have Jordan blocks instead of?
Oh, because you see this condition, I minus lambda j cannot be an integer. In particular, it cannot be 0. And so what I'm assuming is that all, like in particular, I'm assuming that all eigenvalues are distinct. So when you have a matrix with all distinct eigenvalues, it's necessarily diagonalizable. So, so this gives you a description of a kind of an open dense subset, a very, very concrete description of an open dense subset of this moduli space. Where is it? This moduli space, and it just has a very, very concrete description. Once you start getting out of this open dense subset and looking at the kind of strata where you have some resonance, then it becomes a little bit more complicated, but the style is the same. You basically need to add correction terms at higher and higher orders of Z. Okay, so questions? You?
Yes. So why can the difference, I mean, by the definition it's fine, the difference cannot be 0, but in the proof we don't really need that.
Indeed, in the proof we didn't need this, so I could drop it, but I want to assume it precisely because of this, because I want to diagonalize. I don't want to have John normal forms. Okay.
Yeah, my question was similar. Just I'm not clear on why we restrict to even the resonant ones, because you made a comment about because A naught has finite number of eigenvalues that we can kind of find a G regardless of this.
Sorry, can you say that again?
You made a comment at the end of before this definition that because A naught has a finite number of eigenvalues, there will always be a K such that like all of the GKs above that.
That's right.
So would not all, like, is this true then for all systems, or not the diagonal bit, but the first part of this theorem?
No, but I mean, you could have a system who, residues, the different, for instance, this would be a resonant system. So I want to exclude systems of this type from my description.
Okay, but why does this not satisfy the first bit?
Because it's a non-resonant system. So, because it's a resonant system. It has resonance.
Yeah, no, I understand that, but my question is like, do resonant systems, because we can find a GK that like looks similar to this?
Sure, yeah, that may be true. Yeah, so now we're beginning with your question. Now we're beginning to explore the complement of this open dense subset, and it's true there are certain subsets of that complement which behave in a very similar way, but they just require more sophisticated treatment. Yeah. So what I'm doing here is I'm kind of simplifying. I'm just excluding this type of behavior from the get-go. Does that make sense? Any other questions?
So if I get this right, this is a dimensional n now?
This is a dimension n. Yeah, that's right. That's right. Exactly. that's precisely what I was going to say next. That you can so what does it take to right? So in order to give an element of this space, what do I need to give you? I need to give you a diagonal matrix which satisfies some conditions, right? So what a diagonal n by n matrix is, how many degrees of freedom is that? That's n degrees of freedom. So I just need to give you n complex numbers, those would be my lambdas, and I just need to ensure that they satisfy some conditions, right? So that means there is a map, an isomorphism, with a subset of c to the n, c to the n, which is given by these algebraic equations. Subset. It's an algebraic subset. It's literally just given by lambda I minus lambda j is not, I guess. So it's infinitely many algebraic conditions, but they're all algebraic conditions. And so this shows you that this moduli space, in fact, has the structure of an algebraic variety. Here's an algebraic variety. You ask what kind of algebraic variety is it? Is it singular? Is it? And all of those are valid questions, which I will not address. But it is an algebraic variety.
And I guess my main question was, what about the whole space?
The whole space.
If we don't restrict, what happens then?
Yeah, indeed. So it's that space does not sit in C to the n. It's more complicated. Yeah. I mean, so I have included in my notes the general statement. So maybe let me just give you like a very small, slightly perhaps imprecise flavor of the general statement, and then we'll break. So this is very much extra, part 3 stuff. So in general, if I have any system like this, resonant or not, then here's one way to construct a normal form for such a system. So you take, as usual, you take the residue, and what you need to do is you need to fix this journal normal form. That's similar to what we did, because I fixed the diagonal matrix, which is the diagonal matrix of the eigenvalues of the residue. So this part is no different, Jordan normal form. And the way I'll write this Jordan normal form is I'll separate the diagonal bit, which I'll call lambda naught, and the nilpotent part. So this is the diagonal. Lambda is just lambda 1 to lambda n, and this is the nilpotent part. This is what gives you the Jordan blocks. Actually, let me just call it lambda. Okay, I didn't plan this very well. Let me just write it like this, where lambda is the diagonal. And so the other thing I need to do in order to get to the statement is I want to order. So this is not just the diagonal matrix of eigenvalues of my residue matrix, but I will put a specific order on these eigenvalues given by their real parts. So ordered by so the real part of lambda 1 is greater than or equal to real part of lambda 2 and so on up to So the statement is that then there is a gauge transformation which puts nabla in a normal form, and this normal form is of the following shape. So the beginning of nabla knot looks very, very similar to the case of no resonance. So it's just like this. This is my lambda. But then once you have, once resonance appears, then you have corrections, which are given by nilpotent matrices. So it's like this. Some power d, and k, z to the k, for some integer d, and nilpotent matrices nk, so d nilpotent matrices nk, satisfying an algebraic relation, which is the commutator with this diagonal matrix lambda produces k times the nilpotent matrix. Yeah. So this is, it's not a particularly difficult theorem, but it's also not completely straightforward. One real difficulty with this theorem is that this is an example of a normal form. The normal form itself has a lot of symmetries. So, the way these nilpotent matrices really depends on how I've chosen my Jordan normal form. And there's a lot of choice. You can permute Jordan blocks. You can permute, if some of the eigenvalues of their real parts are coincidences, and I will be able to permute those blocks as well. So there's a lot of non-uniqueness about this normal form. That makes it a little bit difficult to write a clean statement, kind of like this here, where I have a very explicit description of this open subset of the moduli space, where I say it's basically the space of all diagonal matrices satisfying a few relatively benign conditions. Here it's just more involved. But I think some people have come up with neat ways of doing this. I just don't remember them. But yeah, okay, let me end here if there are questions. Yeah?
Is D bounded by something?
Yeah, D in fact is, it's something like, I forget, did I write the exact bound? No, I forgot the exact bound, but basically you take all the eigenvalues, number 1, number n, you consider their differences, and you sorry, let me look at my notes. I don't want to say something completely nonsensical. But yes, it's basically given in terms of the largest possible integer that could separate the eigenvalues, something like that. And you can think of it, looking back at the proof that we were doing order by order. Remember, at order 1, I had to make an assumption that no eigenvalues differ by 1, right? And that allowed me to get a gauge transformation which killed that satisfied that equation, or I think I called it. But if I didn't make that assumption, right, then I would have to sacrifice something. I would not be able to produce for you a matrix G1 which satisfies that equation, but maybe I would be able to produce a matrix G1 which kind of kills most of that equation, but not everything. And that is exactly what happens. That not everything that gets killed gets put together into a nilpotent matrix. And so same thing at order 2. You know, if there's no resonance at order 2, then I can produce a matrix G which kills everything, and so there would be no nilpotent matrix at order 2. But if there is, then I have to make a sacrifice and kill as much as I can. Whatever I cannot kill, I put it into a nilpotent matrix. That's the idea.
So this is also some sort of algebraic variety, because everything is algebraic?
Absolutely, yeah, absolutely. It is an algebraic variety. It's just
the dimension is much bigger.
Yeah, the dimension is. Well, no, actually, I don't think the dimension. The dimension is not much bigger. The dimension is the same. Why is the dimension the same? It's because we've just described an open dense subset.
Okay. Yeah.
It's just not. It doesn't sit inside C to the n. It's not an affine variety.
Okay.
It's more complicated, yeah. And if you really want to be very pedantic about this, none of these are actually algebraic varieties. I'm making a simplification. They're actually stacks, because that quotient has always has non-trivial stabilizers. So you really should treat it as a stack. But I'm sweeping after the voluminous carpet. Right, any other questions? All right, okay, so let's end here and then we'll resume tomorrow with irregular singularities.